Good morning, my dear students of Standard 9. We are talking about Chapter 3 of your chemistry book. Last class, we had learned the electronic configuration of atoms, where the electrons are configured on different subshell of the atom. Now, today, we will learn some exceptional electronic configuration. Dear students, last class, we had learned the electronic configuration of the atoms from 1 to 20, where we had learned why the last electron of potassium and calcium goes to 4th energy level without fulfilling 3rd energy level. But there was no exception. Dear students, already we know what is electronic configuration. The arrangement of the electrons in different orbitals is called electronic configuration or electron distribution in an atom. Now, rules of writing electronic configuration. The electronic configuration of any element can be written by following the Aufbau principle. Aufbau principle, that is the electrons at first go to lower energy shell, fulfills it, then it goes to higher energy shell. It is Aufbau principle. And the electronic configuration follow this rule. And for some elements, this rule, the electronic configuration is deviated from this rule, this Aufbau principle. And from there, we had learned that the sequence of the energy level of different subshell is calculated by drawing this. And here, the lowest energy subshell is 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. And if you can draw this, then the sequence of the energy level of different subshell can be written from there. Now, from there, the electronic configuration of iron can be written. Look, the lower energy shell 1s, then 2s, now 2p, 3s, 3p, 4s. In this way, you will write. Now, you will fulfill the subshell by its electron holding capacity. S orbital can hold maximum 2 electrons, so it will be 1s2, then 2s2. P orbital can hold maximum 6 electrons, so it will be 2p6, now 3s2, 3p6, 4s2. Now 6 electrons are left. After 4s, the orbital 3d comes, so it will be 3d6. Now dear student, look, the subshell 3d, it belongs to 3rd shell, and 4s, it belongs to 4th shell. So we will write this electronic configuration in this way: 1s2, 2s2, 2p6, 3s2, 3d6, 4s2. Dear student, the last electron goes to 3d orbital, but we will arrange the electrons like this way because on their shell, on their main energy level. And the electronic configuration also can be written: first shell there are 2 electrons, second shell 8 electrons, third shell 8 and 6, total 14 electrons, and fourth shell there are 2 electrons. So the electronic configuration of iron is 2, 8, 14, 2. But you have to write the electronic configuration on this way, and it follows Aufbau principle. In this way, the electronic configuration of every atom can be written. Now, another any atom we can write. Now suppose this is bromine. The atomic number of bromine is 35. So at first you will arrange the subshell from there: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. In this way you can write, and you will write the electrons on this subshell: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, because the maximum electron holding capacity of d subshell is 10. Now 5 electrons are left. You will count the electrons from here: 2 to 4, 6, 10, 12, 18, 20, 30. Now 5 electrons are left. So after 3d orbital there is 4p. So now it is 4p5. Now look, the orbitals are not arranged here. So you will arrange the orbitals and it will be 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, 3d will come, 3d10, 4s2, 4p5. And the electrons of different orbit, that is on the first shell there is 2 electron, second 2 and 6, 8, third shell 2, 6, 8, 10, 18, and on the fourth shell there are 7 electrons. So 2, 8, 18, 7. This is the electronic configuration of bromine. In this way, we can write the electronic configuration of tin also. Tin 50. The atomic number of tin is 50. So from there, you will write the subshell 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. The subshell you will write up to which you need. Okay. 5s, then 4d, 5p, 6s. In this way, they will come. So now you will fulfill the subshell by its electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and up to this 4d10, 48, and the rest 2 electrons it will go 5p2. So now we will arrange this subshell. 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, 3d will come, 3d10, 4s2, 4p6, then 4d will come, 4d10, 5s2, 5p2. So the electronic configuration of tin will be 2, 8, 18, 18, 4. This is the electronic configuration of tin. Now dear student, you can write the electronic configuration of every atom by drawing the sequence of the orbitals. Okay. Now I will show you the electronic configuration of the atoms from 21 to 30. That means scandium to zinc. The electronic configuration of element from scandium to zinc is written here. Look, scandium 1s2, 2s2, 2p6, 3s2, 3p6. At first it was 4s2, but here it is written by arranging 3d1, 4s2, and it will be 2, 8, 9, 2. In this way, titanium, vanadium, these are written. Look here, the electronic configuration of chromium 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Dear student, look here, there is one exception. What is this? It should be 3d4, 4s2, because the electrons at first go to fourth shell, 4s orbital. So it will be 4s2, and the rest 4 electrons will come to 3d orbital. So it should have 4 electrons and it will be 3d4. But the electronic configuration is written 3d5, 4s1. That means it is wrong. No, it is not wrong. There is one exception of this above principle. Today we will learn this exceptional electronic configuration that is done for chromium. Here manganese, iron, cobalt, nickel, all they follow the principle, and here all the electrons at first go to lower energy shell, then it goes to higher energy shell. But here for copper there is again exception. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. But it should be 4s2, 3d9. That means 3d9, 4s2. But there is again exception. This exceptional behavior we will learn today. We had seen the electronic configuration of chromium and copper. There are some exception. This type of exception also for some more elements, and today we will learn for this. We will learn why this exceptional electronic configuration is occurred. Deviation of electronic configuration from the general rules. General rules means general rules is that the electrons at first go to lower energy shell, fulfills these, then they will go to higher energy shell. But this General rules are deviated for some atoms. Today we will learn this deviation. The electronic configuration of almost all elements can be confirmed by Aufbau principle, but there are some deviations noticed for a little amount of elements. To measure reasons behind these deviations are as follows. One is more stability of half-filled and full-filled orbitals. More stability of half-filled and full-filled orbitals. And second one is very small difference of energy between NF and N plus 1d orbitals. This deviation we will learn in our 11-12 classes, but this deviation we will learn today, that is more stability of half-filled and full-filled orbitals. Dear students, except S, other three orbitals P, D and F, they are called degenerate orbitals. P, D and F are called degenerate orbitals. And there is one thing, that the degenerate orbitals will get more stability when they are half-filled or full-filled. That means the maximum electron holding capacity of p orbital is 6. So P3 or P6, it will be more stable configuration. In this way, D5 and D10, half-filled and full-filled, this electronic configuration is more stable. In this way, F7 and F14 are more stable. Today we will learn about this. And for these half-filled and full-filled orbitals to become half-filling or full-filling d orbitals, the above exception for chromium and copper was observed. Now, more stability of half-filled and full-filled orbitals. Degenerate orbitals, I told P, D and F, these are called degenerate orbitals. Degenerate orbitals gain more stability when they are exactly half-filled or full-filled with electrons. Like NP3, N means 2, 3, 4, 2p3, 3p3, 2p6, 3p6, in this way. ND5, ND10, NF7, NF14, these are half-filled and full-filled condition. Did you understand this? NP3, that means half-filled p orbital. NP6, full-filled p orbital. ND5, half-filled d orbital. ND10, full-filled d orbital. NF7, half-filled f orbital. NF14, full-filled f orbital. These configurations are more stable. For this reason, the configuration N-1 D5 NS1, that means it may be 3d5 4s1. N minus, that means when n is 4, then it will be 3d5 4s1 or 4d5 5s1, 5d5 6s1, in this way. N-1 d5 ns1 becomes more stable than N-1 d4 ns2. That means for chromium, if the electronic configuration is 3d5 4s1, then it becomes more stable than 3d4 4s2. And in the same way, the configuration N-1 d10 ns1 becomes more stable than N-1 d9 ns2. For example, copper. For copper, if it was 3d9 4s2, it is less stable. So 3d10 4s1 becomes more stable than 3d9 4s2. And for this type of deviation is noticed for some elements. Therefore, the deviations are noticed in the electronic configuration of chromium, copper. Look, in the periodic table, just below chromium, there is molybdenum. Molybdenum, silver, just below copper, there is silver, there is orium also, etc. because in these elements the last electron before fulfilling the lower energy shell goes to higher energy shell to make them stable by half filling or fulfilling the degenerate orbitals. For this electronic configuration, the electrons without fulfilling 4s or 5s orbitals, they go to 3d or 4d orbitals to make them half-filled or fulfilled for becoming stability. So, the electronic configuration of chromium, copper, molybdenum and silver are as follows. The electronic configuration of chromium should be this, isn't it? 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. It is the general rule. But if one electron from 4s orbital goes to 3d orbital, then it becomes 3d5 and it becomes 4s1. And 3d5, that means d orbital is half filled, it will be more stable configuration. So, if the electronic configuration is this 3d5 4s1, then it will become more stable. So this is the correct electronic configuration and this is the wrong electronic configuration. And here is the deviation of Aufbau principle, deviation from the general rules. Same for copper. The electronic configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. But if the d orbital gets one electron from 4s orbital, then it will become fulfilled, and we know the degenerate orbitals, when they become fulfilled, they will be more stable. So the correct electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. It is the correct electronic configuration and it is the wrong electronic configuration. In the same way, if we write the electronic configuration of molybdenum, its atomic number is 42, then it will be 1s2, 2s2, 2p6, 3s2, 3p6. Here I have written it by arranging the orbitals 3d10, 4s2, 4p6, 4d4, 5s2. It should be the correct electronic configuration, but here the electronic configuration will be 4d5, 5s1 to become the 4d orbital half filled. So this is the correct electronic configuration and this is wrong. In the same way, the electronic configuration of silver, its atomic number is 47, 4d9, 5s2, but it is not correct. The correct electronic configuration is 4d10, 5s1, because if one electron from 5s orbital comes to 4d orbital, then it will become fulfilled, and the fulfilled d orbitals make the atom more stable. So it is the correct electronic configuration and it is wrong. So dear students, only for these 4 atoms you will read the exception, and from 1 to 50 the electronic configuration you will write in home. There are only exception for these 4 atoms from 1 to 50. So you will write the electronic configuration, you will practice writing electronic configuration from 1 to 50. Now we will learn the electronic configuration of ions. Ion, it may be cation or anion. You know, when electron is released from an atom, then the atom becomes positively charged ion or cation, and when electron is added to an atom, the atom becomes negatively charged ion or anion. So the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. Now when electron is released from sodium atom, it will be sodium ion, Na+. Dear student, you have to remember one thing. Electron will be released from the last shell, not from where the electron comes at last. Just you have to remember this. when an atom will release electron to become cation, then from the last shell electron will be released. And when an atom accepts electron, then also on the last shell the electron will be added. Here the last shell is 3s and there is only one electron. So the electronic configuration of sodium ion is only one electron is released. So it is 1s2, 2s2, 2p6. In the same way, chlorine 1s2, 2s2, 2p6, 3s2, 3p5. Chloride ion, negative ion, that means one electron is added with it. So it will be, the last electron will be added on the 3p subshell. So 1s2, 2s2, 2p6, 3s2, 3p6. This is the electronic configuration of chloride ion. Now, the electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Dear student, look here one thing. The last electron comes on d orbital, isn't it? The last electron comes here. But when chromium will release electron, it will release from 4s orbital at first. But the ion, chromium ion Cr3+, that means total 3 electron will be released from here. So the first electron will release from 4s orbital and second and third electron will be released from 3d orbital. So there will be 3d3, 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. Electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. So when iron will release 2 electrons, then it will make ferrous ion Ap2+, and when iron will release 3 electrons, Ap3+, ferric ion, then 3 electron will be released from the last shell. Now look, on the last shell there are 2 electrons. Here the last electron comes on d orbital, but when 2 electrons will be released from iron, then these 2 electrons will be released from last shell, 4th shell, that means 4s orbital. So the electronic configuration of Ap2+ will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. And when ferric ion will form, 3 electrons will be released from iron, then 2 electrons will be released from 4s orbital and 1 electron will be released from 3d orbital. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Dear students, look, there are 2 ions, ferrous ion and ferric ion. And on ferrous ion, there are 6 electrons on 3d orbital, but for ferric ion, there are 5 electrons on 3d orbital. There are 5 electrons here, and we know when the degenerate orbitals are half filled or full filled, they become more stable. So here 3d is half filled for ferric ion. So comparatively, ferric ion is more stable than ferrous ion. Okay. Now the electronic configuration of copper. This is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1, because this is our exceptional electronic configuration. So you will write this electronic configuration. You will never write 3d9, 4s2. Always you will write 3d10, 4s1. Now copper, it has also 2 ions, Q+ ion and Q ion. When 1 electron is released, then Cu+, that is called Q+ ion, and when 2 electrons are released from copper, then Cu2+ will make, this is called Q ion. So 1 electron, it will release from where? Obviously from 4th shell, from 4s orbital. So Cu+, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. And when 2 electron is released, then after releasing 1 electron from 4th shell, the second electron will be released from 3d orbital. So it will be 3d9. Like iron, here also there are 2 ions, Q+ and Q prick, and for Q+ ion there are 10 electrons on 3d orbital, but for Q prick ion there are 9 electrons here. So it is fulfilled d orbital. So Q+ ion is more stable than cupric ion. So dear student, today up to this you will practice writing electronic configuration, and while doing the electronic configuration of ion, cation, you have to remember one thing, that the electrons will be released from the last shell. So thank you everyone. Goodbye to all.